This is kind of a strange topic in the IB syllabus because deduction and proof is not something that you can test in an isolated way. You have to be proving something, you have to be deducing something about some other topic of math. But it is an isolated point in the syllabus 1.6. So I'm going to start by asking you about these things, and you can see that they are slightly different because there's a number that has changed. And I want you to think about what is the difference between these two things. What are they? Are they the same kind of thing? Pause the video, think about your answer for a little bit before I tell you. So this one here is an equation. And the things about it that tell me that it's an equation are basically the fact that it has an equal sign and that it has a variable. But those can't be the only two things because this one also has both of those. And I'm really trying to suggest to you that they are not the same thing, they are different. So there is an extra thing that is very important in order for us to say that something is an equation, which is what we want to do with it. We want to solve the equation. And solving an equation means finding the values of x that satisfy this equation. In other words, the values of x that actually make the left side be equal to the right side. Because if you pick a random value of x, like 10, for example, and you plug it in for x, it's not going to give the same number on both sides. So 10 is not a solution to this equation. And whenever we have an equation, we really do want to solve it, which means finding the values. And we can solve this one right now. It's not a particularly difficult one. I put the word values in plural here because in general, equations can have multiple solutions. And in fact, most people look at this one and suspect that it's going to have two solutions because there is an x squared over there, so it looks like a quadratic equation. But when I start to solve it, the first thing that I want to do is to distribute this multiplication on the right side. And then the x squares are going to cancel. I can subtract x squared from both sides of the equation. I can also collect these two here because they are like terms. And I'm also going to add 6 to both sides of the equation. So x equals 2 is the only solution to that equation. What is different about the other example is that it doesn't just have one solution. Quite the opposite. I'm stating a fact that is always true. This is one of the special products. A plus b times a minus b is a squared minus b squared. So although it does have the equal sign and the variable, we don't want to solve it. So that is different. That is not an equation. The thing that we want to do with it kind of determines what kind of thing that it is. So that's called an identity. It's true for all values of x. So what do we do with it? We don't want to solve it because there's no value of x to find. So there are things that we can do with identities. One very useful thing is to apply it in order to do something else. In order to solve an equation when you have something like this, you can substitute it by something like that or the other way around because they are equal. So identities are useful in solving other equations. They are tools. But as for exam questions, they will usually ask you to prove that such an identity is true. So that's another piece of information that you can use to decide if the thing you're looking at is an equation or an identity. It is largely about what you want to do with it, and the question will tell you what you're supposed to want to do with it, right? So if it says find x, oh, then that means solving it, so this is an equation. And if they say show that, which is the topic of this video, we are going to want to prove that this is actually an identity. In terms of symbols, there is another one that people sometimes use here to distinguish one from the other, which looks kind of the same, but with 3 horizontal thingies instead of 2. But the thing is that exam questions are really inconsistent about using that. They don't always do this. So I wouldn't count on that to distinguish both things. It really is about context, about what you want to do in the question. It's not that they couldn't use an equation in a show that question. They could, but it would be a little bit different. Instead of saying find x, they could say show that x equals 2. And as a student solving the question, what you're supposed to do here is exactly the same thing as we had just done before, which is solve the equation. Maybe solve it a little bit more slowly than you normally would. As you can see, I've done all of the same steps as I had before, but I've made them a little bit more explicit. I never did 2 steps in the same line. And the reason why I'm doing it this way is to avoid any possibility that the person who is grading my test is going to have any doubt that I actually know what I'm doing. that I'm not just saying that the answer is x equals 2 because I know that that's the answer because that was given in the question. So you have to do it extra slowly to make sure that they understand that you're actually doing it. If you do steps in your head, then that's indistinguishable from just copying the answer. So those are the first two very important points, and those are valid for any question where the verb is show that. But the example that we just did was show that x equals 2, and then it was about solving an equation. But how would all of that work in showing that an identity is true? So in the case of an identity, how does this apply? Because what's going to be considered the answer here? What's going to be playing the role of the x equals 2 in the first example? And it's like this. For an identity, you have the left side and you want to show the right side. So this is the thing that you have and you want to show that that's equal to this. So you're going to work from left to right. You can't work with this as an equation, like doing the same operation to both sides. That's not what they expect you to do. They expect you to just copy the left side, manipulate it on its own, and then as a conclusion in the end, you will finally, after a bunch of slow steps, you will finally reach a line that is equal to the right side of the original thing. Now, when they write this in the syllabus, they do say left to right or vice versa, but I am not confident at all that that would be acceptable as an answer, okay? That you would start here and get there. I am not sure. I would rather not do that as a student. I prefer to always go from the left to the right because then I know that I'm going in the correct direction and I know that my answer will be accepted and will get the marks. Even though a lot of times there's one direction that would be easier. For example, if I wanted to start here and get here, I would just do the distributive and things would naturally cancel out. I would be there. Unfortunately, this question has been posed in this direction, so I want to start here and go there. And listen, it's always possible. If the two things are equal and there is a sequence of steps that takes this one to this one, then there is a sequence of steps that also takes this one to that one. You just have to write it in the correct way. You have to write it in the correct order and slow enough so that it doesn't look like you are just copying the answer. So you can kind of think backwards, just don't write it backwards. And what I'm thinking is that this is going to be a distributive and some terms are going to cancel out. And I want to write this backwards. In order to write this backwards, I have to make the terms appear from out of nowhere because that's the opposite of when they cancel out, they disappear. Now I want them to appear from nowhere. You don't have to do it quite as slowly as I'm doing it right now, okay? But I'm just adding a 0 there because adding a 0 doesn't change anything. So I am definitely allowed to add a 0 over there. But I'm doing that to justify where this 2x minus 2x came from. Because 2x minus 2x is 0, so I'm just putting it in the place of the other 0 that had actually appeared from out of nowhere because it is a 0. So now I'm still thinking in terms of distributive. I want to see that distributive happening backwards. And distributive backwards is factoring things out. So what can I factor out here? Well, nothing from all four terms. But if I look at just the first two terms, they both have x, so I can factor out just the x. And as for the other two terms, they are both negative, so I'm going to put a minus here and both of the terms in a parentheses. But now you see that they both have a 2, right? So I can factor out a 2 from there as well. So now I have just two terms coming from four smaller terms that I used to have. But both of these terms have a very nice looking common factor, which is the x plus 2. And since that is a common factor of both of my terms, then I can factor it out. And that's it. I have reached the point that I wanted to reach. I am probably exaggerating in the slowness, but the thing is that I want to show you how to be extra safe and that these things can be slowed down. Now, also important to mention about these kinds of exercises is the common mistake that people tend to do. Because the common mistake in the previous exercise, when it was show that x equals 2, in that case, it would be wrong to just take x equals 2 and substitute that into the equation, check that it works. That would be a very common mistake. You're not supposed to use the thing that you want to show. But over here, there is a different common mistake, which is trying to show examples of x's that work. Because they all work. The identity is true for all values of x, so it's going to be pretty easy to find examples. But examples don't prove anything. So if you're just doing examples, it's the same as you're doing nothing, and you're going to get 0 marks for that. Now, does that mean that you're not allowed to do examples? Not really. This identity is quite easy. We recognize it as a special product, but sometimes we want to prove an identity that we are not very sure about. We are questioning, is this even true? So in this case, it can be helpful to do a couple of examples just to convince yourself that the thing actually is an identity. Maybe you kind of, through the examples, see how it sort of works. But that is just to organize your thoughts. That is not a part of your solution that is going to receive any marks. You don't even have to cross it out if you don't want to, but it's just not where the marks are going to be. So just to show you what that would kind of look like, but that's wrong, okay? So the student would pick his favorite value of x. Like if x equals 3, then, and then he plugs in x equals 3, gets to this, simplifies it. Yes, 5 is equal to 5. That's working. And then maybe he doesn't think that one example is enough, so he does a second one. The second example also works, obviously. Any example is going to work because the thing is an identity. But this is not showing anything, okay? This is wrong as a way of solving a question. So that gets 0 marks. Of course, the calculations are not wrong, but that's not how you solve a question. So I mentioned at the beginning of the video that the strangeness of this topic is that you can't really test proving in isolation. You have to be proving something, and something is going to be about some topic of math. Sometimes it is going to be show that the derivative of this function is this other function. And then how do you do that? Well, you just do the derivative, showing all of the steps very slowly. But there is one specific type of question that they like a lot, so it appears a little bit too often, which is designed to test proofs in isolation. Like the question is not about anything else, it's just about proofs, except it has to be about something. So the way that they tend to do that is by saying statements about odd numbers and even numbers. Because supposedly odd numbers and even numbers are such a basic thing that it doesn't even count as content. Except that it is content, because it's totally possible that you, like everybody else, know what an odd number and an even number is, but if you've never seen them written down this way, if you've never thought about the fact that any even number is twice as much as another integer because it's divisible by 2, and therefore it can be written as 2 times k, where k is an integer. This is a generic way of referring to all of the even numbers. And what about the odd numbers? The odd numbers are all of those that are not even. Well, I mean, all those integers that are not even. So the way that we do that is we take the even numbers and we shift them by 1 to one side. So it's like 2, 4, 6, 8. Now it's 3, 5, 7, 9. All of those are odd, so that's why I'm writing them as twice of somebody else plus 1. The plus 1 is this shift that takes it actually away from the even numbers. You could shift it to the left instead. 2k minus 1 is a different way of writing down a generic odd number that also works. And depending on the question, you are going to want to do that. Another thing that they use constantly in this kinds of question is talking about consecutive number. Consecutive means the ones that are right next to each other, right? Like 6 and 7 are consecutive numbers. But 6 and 7 is an example, and examples don't prove anything. So I can't just say 6 and 7. I have to say k and k plus 1, for k is an integer, of course. That takes care of all pairs of consecutive numbers, the 6 and 7, 7 and 8, all of them. If you want 3 consecutive numbers, you could say k, k plus 1, and k plus 2, but it's just a little prettier, a little bit more symmetric to say k minus 1, k, and k plus 1. So that is the way that people usually do it. Sometimes they will ask you something about 2 consecutive even numbers. And of course, consecutive numbers can't be both even, like 6 and 7 and 7 and 8 always. One is even and the other one's odd. But when they say consecutive even numbers, it's like 6 and 8. It's an even number and the next even number. So that's going to be 2k and 2k plus 2. If you want 2 consecutive odd numbers, again, something like 7 and 9, where you skip the even number in between, then it could be 2k plus 1 and 2k plus 3, but it's a little bit prettier, again, because of symmetry, to just say 2k minus 1 and 2k plus 1. So you take an even number and the 2 odd numbers that are around it. Now, if they want 2 odd numbers, but without saying the word consecutive or without saying anything else about it, any restriction on what's 2 odd numbers, then people are tempted to say things like 2k plus 1 and 2k plus 7, both of which are odd numbers, so that is a pair of odd numbers, but it's not general enough. When they say two odd numbers, you can't specify that the distance between them is going to be 6. But when you say 2k plus 1 and 2k plus 7, that's exactly what you're doing. You're specifying that the distance is always 6. So if you want more generality here, just any two odd numbers, there is no way to do that besides using one more letter. They can't both be k. So something like 2k plus 1 and 2j plus 1, a completely different letter. And the kinds of statements that they're going to have you prove about this content are generally very stupid statements, like prove that any two odd numbers added together is an even number. You know this is true, right? You've known this is true probably like since fifth grade or something. But now I'm asking you to prove it. Prove this very simple fact that everybody knows. And then this kind of question makes people uncomfortable, and rightly so, because you go, well, of course it's true. Like 5 plus 7 is 12, 1 plus 11 is 12 also, 3 plus 15 is 18. Any two odd numbers that I add are going to be an even number in the result, but I am only giving examples, and examples don't prove anything. When I ask you to prove something, you need to do it in generality for all pairs of odd numbers. And that is why we were just talking about how to write things in generality, to make sure that we're not giving examples. We are working with a variable that stands for all of them. So that's actually going to be proving it, because it's going to be all of them. So the more obvious is the thing that you're trying to prove, the more difficult it's going to feel to prove it, because it's obvious. So what do I even write down? You write things down very slowly. You show the examiner that you know about these things. So I know what an odd number is. I know that I have to pick another one with a different letter. I understand that you want me to add them. And now comes the easiest part of this proof, because we are back in comfortable, familiar territory. We are numbers and letters and symbols and calculations. Just added the 1 plus 1 equals 2. And now I'm going to factor out a 2, which is what makes this an even number. This is the conclusion that I wanted to reach, that this is even. And now I have to say that I know this in order to complete the question. And again, yes, I am probably saying too many words. I am probably exaggerating in how explicit I want my knowledge to be. But the fact that I am exaggerating for doing too much doesn't mean that you should exaggerate to do too little, okay? Somewhere in the middle is the right amount. And if you do too much like this, you obviously get all the marks. And then sometimes they start trying to help you by splitting the question in parts A and B. And that is not always successful as help. Because in this example, if there was no part A and they just straight up asked me, show that the sum of the squares of two consecutive odd numbers is even, I would start the question by taking two consecutive odd numbers, which we have talked about before. The standard way of writing two consecutive odd numbers is 2n minus 1 and 2n plus 1. I would take their squares, which is what he's talking about, and add them. And then I would start doing things to this. But because there is a part A, if I just do this, it doesn't look like I know what I'm doing. It looks like I'm just copying from part A. So now I feel compelled to write words to explain to him, look, I do know what I'm doing. I'm not just saying this because you said it. I know why you said it. It's because it is the sum of the squares of two consecutive odd numbers. And now comes the easy part of the question, which is manipulating this. I'm going to start by using the special product on both of these things, but I'm going to do it slowly because things are going to cancel out, and I don't want it to look like I'm just forgetting the terms that are going to cancel out. So first I'm going to actually put all the terms there, because this type of question also serves to check that you don't mess up special products. I am also leaving the parentheses here just for clarity and the slowness of what I'm doing, to make sure that this is this and this is this before I cancel this one out with this one. Because you see, if I had forgotten them, if I had incorrectly said that this plus this squared is this squared plus that squared, I wouldn't fail to reach the conclusion that he wants me to reach, but I would be wrong anyway, because I would be messing up special products. So I do have to show all of this on the page. And this is 8n squared plus 2, which was part A. Part A is this part here. But for part B, I have to do it a little bit more because I need to show that this is even. I am going to do this in the exact same way that I just did in the previous exercise by factoring out a 2 and commenting about why this makes it an even number. Now, in this question, again, he has split it into part A and part B in order to try to help you. But in this case, I think it did help. Because if he didn't say part A, if he just said, show that the square of any number is this or that, I don't know that a lot of people would have thought of splitting all of the numbers into 4 categories according to their remainder in the division by 4. Maybe that idea would have occurred to some people, but definitely not to most people. And that is what he's telling you in part A, that this is how you're supposed to do it. So if I remember correctly in this question, part A was like 2 marks and part B were like 6 marks. In any case, yeah, explain why an obvious thing is an annoying question, but don't take it too seriously because it's just 2 out of a lot of marks and it is only there to help you to do part B. So anything vaguely coherent that you say will probably be accepted for the 2 marks. So you can just say some sentence about the remainder in the division by 4. Okay, numbers are either divisible by 4, which are the 4k, the multiples of 4 that leave no remainder in the division. But in case they are not divisible by 4, then there will be a remainder, and this remainder will be either 1 or 2 or 3 because it doesn't make sense for the remainder to be bigger than the thing that you're dividing by. And yes, these are just words. So you put the words on the page and you get your marks. The interesting part is what happens in part B, because I have already told you that examples don't prove anything. And what's going to happen here is going to feel a lot like doing 4 examples, because I am going to take this, and that and square each one of them to see what happens. That is literally all that I'm going to do. But they are not examples. They are 4 categories that together have all of the numbers in them. So they are not examples. They are actually all the numbers. They've just been split into 4 categories in a very smart way. They have done the smart part for you when they wrote part A. You just have to calculate. Even if you don't really know what's going on with all of this deduction stuff, if you have only a vague notion of what it is that's happening in the question, there are still some marks to be had here. So don't give up on questions completely, okay? Squaring things correctly is clearly already some of the marks. And now I need to factor out a 4 in each of them. I know that because I want the format in the end to be 4t and 4t plus 1. So there's a 4 that I'm going to factor out whenever I can, which is in the first one and the third one. All of the terms have a 4, which makes them into numbers of the form 4t, which is one of the ones that we wanted. Now the other one that we want is 4t plus 1. And over here, it's very clear where this 1 is going to come from, because the other 2 terms have a 4 that I can factor out, but the 1 doesn't, which is fine because that's exactly what I want, right? 4t plus 1. That's the other format that I wanted. And in the fourth line, the kind of the same thing is going to happen, except that you have to look at the 9 as 8 plus 1, because then the 8 does have a 4 to factor out together with this and the 1 is going to just stay there. Technically, this was a type of proof that people refer to as proof by exhaustion, which does not really refer to the fact that you are exhausted by the way that you get to the end. What's exhausted here is not really you, it's the examples. It is a proof by exhaustion because we have exhausted all of the possibilities for what any integer could be. And for all of the only 4 possibilities, we have proven that the thing that we want actually works. So if it works for all of the possibilities, then it works always. So proof by exhaustion actually means testing all cases. It has to be done in a smart way because all cases, in the case of the integers, is an infinite amount of numbers, right? So you're not going to be doing infinite things, but it is categorized. There are other types of proofs that have nice names that exist that people do. But as for the standard level of the course, this is as far as it goes. There are other types of proofs in the high level course, but I'm going to stop this video right now.